Morning, everyone. So yesterday we started looking at ionic nomenclature, naming of ionic compounds. One good way of just sort of recognizing the compound itself to be ionic. So far we've been saying ionic is made out of a metal and a non-metal. The metal always comes first. On our periodic table here, we know the metal. We picked one of them on the left-hand side of the table, and we mix and match it with one of them on the other side of the stair step. So metal and non-metal ends up forming an ionic compound. We'll need to qualify that definition a little bit in our course, but for the time being here, that is a good way to recognize it. In this case here, for an ionic compound, we had the fact that charges in general are unstable. So we had the whole notion, the sum of charges actually had to cancel out. Unfortunately, on our periodic table, they don't actually give us the charges like on your grade 10 table. So what we did yesterday is we started memorizing some of the group trends here. Group number 1, so ignoring hydrogen. Group number 1 were your alkali metals. These ones here were all +1 when they're bonding. Alkaline earth metals from beryllium down to radium there. That one there is all going to be +2. I basically need to work out the charges so that the charges end up canceling out. Just going to go through just a little bit more detail here on the whole nature of an ionic compound. We're going to get back to some naming afterwards. An ionic compound here is said to form a lattice. So let me do one as an example here. Let's go back to the lattice of, let's do potassium. So let's say I want you to write the compound potassium in bonding with chloride. So potassium chloride. So we have the word name. We're expected to write the IUPAC name here. It has the metal first. Potassium, it's the symbol K, so capital for there. Chlorine here is going to be chloride, actually comes from the element chlorine, so we have Cl there. Because these ones here are bonded, I do want to worry about the charges. Potassium here is a +1, a chlorine here is a -1. Well, what ratio would I need so that they can cancel out? Oh, this is perfect. +1 already cancels out as -1, therefore I write the compound as KCl. However, just a little bit more detail for this ionic compound here, I want you to just make this note here. All ionic compounds, they form what are called crystal lattices, or just lattices for short. So in some sense here, what I'm describing here, what is a lattice? A lattice is actually a structure that is a repeating positive and negative structure. So what's happening here is, although I wrote my compound, I worked out the charges, +1, -1, they cancel out, KCl. In fact, sometimes they're actually greedy. What's actually happening here is a K being an alkali metal has 1 valence electron. Chlorine actually has 7. Again, we'll get into all these details later on in our course. When they collide, they potentially can play around with the unpaired electrons. Chlorine is actually so much more electronegative, it's so much more of a bully that chlorine actually completely steals the electron over. That's why in this case here, we actually get a full electron transfer. K has completely lost an electron. That's why K has become a plus. I put a square bracket around it and put it with the plus in the corner there. Chlorine here itself used to be neutral, right? And now it's picked up potassium's electron. That electron looks identical to the electrons that I actually have. There we go, we actually get the negative charge. So that's actually where the +1 and -1 comes from. It's because that electron actually got transferred. However, like I've been saying, charges are unstable. So if I suddenly have a K+, it actually only needs 1 Cl-, and it's already counterbalanced. Perfect. So that actually is nice and happy. But we know charges like positive always attracts negative, even though I only need the 1 chlorine neighbor to completely stabilize me. The potassium is really greedy here and says, because I'm positive, I want to surround myself with as many chlorines around as I can. The chlorine here is negative. In a similar fashion, opposite charges, they're going to surround themselves with as many positives around as they can. Because ionic compounds have these charges, this is always going to happen. Now, it's not always going to be necessarily exactly one on top of the other. Sometimes they pack together in a different orientation, but we will eventually have this lattice structure. It will end up repeating. Sure, the simple molecule was just KCl like that, but because of these charges, because like charges always attract opposite charges, they're going to surround themselves with as many of the opposite charges possible. So we're going to end up forming this repeating structure, which we call lattice. So this ends up repeating over and over and over again, also in 3D, in that shape there. So all ionic compounds form lattices, and this actually will come back to later on. This is actually why ionic compounds are typically solids at room temperature. Because we have a lattice, we have many attachments. We have many bonds holding this together. You're going to need to heat this up quite significantly for these ionic bonds to actually break. Now, the problem for us here is, well, we won't actually know. Maybe there's trillions and trillions of potassium and chlorine, even more than that. Well, we're going to come back to the fact from yesterday. I worked out the charges. For every potassium, it has to have one chlorine neighbor. Well, what about this potassium here? Well, it has one chlorine neighbor. What about this potassium? Well, it has one chlorine neighbor here. I'm just going to indicate to you here is actually the ratio. I know realistically, because we end up forming a lattice, it's like K 1 gajillion, chlorine 1 gajillion. But I know we're going to actually call this a formula unit. A formula unit here is like a Lego piece. So if I had a Lego piece of just 1 K and 1 Cl, and I just copied and pasted that and I repeated that through the entire structure, I would get the rest of the compound. We see that this ratio here, K1Cl1, it's implied there's ones if I don't write anything there. It's implied that's actually the ratio. This is the ratio in the lattice. And that ratio here is going to have some measure on how easily things pack together. That's going to affect the melting point later on. But that's important for you to know. An ionic compound, even though we just say, oh, KCl, we never really mean just 1K, 1Cl. Because of these charges, we expect all of them to form these lattice structures. So just watch out for that. That's true for all ionic compounds, even if I throw in those polyatomics. It was nice for our group trends here. I can say alkaline metals +1, +2. These ones here are going to be transition metals. So these ones here are multivalent. You will have a handful of these transition metals here on the back of your grade 11, grade 12 table. There's a handful, like iron can be 2 or 3, chromium can be 2 or 3, manganese 2 and 4. You can't really predict those. They just picked out a couple of them there. You can find them on there. For metals, if you have to guess, this is just a general trend. As you start looking at the Bohr models, we're going to find aluminum's column is sort of 308. So if I had to guess for the metals, so for the ones that are on the low side of the stair-step line, I would imagine these ones here are +3. I would imagine these are +4. These are +5. But those ones here only apply to the metal side of it. What about the non-metal side of it? For the non-metal side of it, we said noble gases, right? Those inert gases, they pretty much keep to themselves. Helium down to radon. It's going to be 0 as a charge. Our halogens here, these ones here have a -1. If you have to guess, oxygen is just the next column over. It's 2 away from noble gas. We can call that -2. These ones on the top here, -3. These ones at the top, -4. That's just a general nice pattern for us here. But we're going to see later on in today's lesson, nonmetals, especially when they bond to themselves, they actually usually form a covalent bond. They don't actually form an ionic bond like we've been talking about. But if you have to guess, if we're trying to make charges with these ionic compounds here, you can use this generalization. How many columns am I away from the noble gases? The nonmetals are a little bit easier because I can see directly the steps here. If you look at the element number, element 3 would have actually been here. Element 11 would have actually been here. It's sort of like this alkali metal family would have been over here. It too is just 1 away, but it has 1 too many, so there could actually be +1 as a charge. So just look out for that there. The hard part in this section here, as we throw in a little bit more variety, is when I give you compounds, they can be all jumbled up. Some of them could have multivalent, some of them could be with polyatomic, some of them are just plain old ionic compounds, some of them are acids, we're going to see in today's lesson. If they're all mixed up, you need to first recognize what type of compound it is and then use the appropriate naming. There's nothing really new to this here, you just want to be practicing. So let me just give you a handful here. Let's say I have CS3PO4, I have TI SE2, I'm going to have NH4, my Chiku again. Let's go the other way as well. Let's do magnesium, dichromate. Let's do palladium, 2 fluorite, and let's do one more, silver, cyanide. Cyanide. Alright, so for this section here, again, a lot of this is reviewed from a junior science class here. you need to be able to be comfortable going from what's otherwise known as the formulas, go from the formulas to the word name, or in this case here, if they give you the word name, see if you can write the symbols, see if you can identify that ratio that's left over in your lattice. So what I would do is I would just pause it, try it out for yourself, try using the table. Eventually, you're actually not given this regular grade 11 table. So eventually, some of the most common ones you also need to memorize, especially these polyatomic groups here down here. But we'll just slowly work up to that. So if you can just pause it here, try naming it for yourself. Assuming you've done that, let's have a look. This one here, CsPO4, when I'm tempted to say cesium phosphorus oxide, it's never so complicated that. It's usually just one part name for the metal bit, one part name for the remaining grouping. Let's look up the CS here. This CS here is cesium. Sometimes they spell it with a CAE, like cesium. It's the exact same. So cesium. Don't say phosphorus oxide. Don't try to name this one by yourself because I recognize this to be a group. I just look on the backside for the time being. The PO4 grouping is the common name phosphate, and I'm just going to copy that name there, phosphate out, and I'm not going to change the ending to IDE. Doing the word name is fairly easy because I'm not having to indicate what ratios I needed. They've already done for you. Well, cesium is the alkali metal +1. Phosphate would have -3. I need 3 cesiums to actually cancel phosphate's charge. That's just a mental check for myself. It's best to say in that formula unit, just drop those charges there. Those charges have already counterbalanced in the ratio that they've canceled. Titanium here is actually a transition metal. So titanium, we would expect, is going to be multivalent. I just noticed we're actually not given titanium here. But because it is a transition metal, it's always good to guess that it's going to have multiple charges. Titanium is using some charge to react against Se. Se is the element selenium, so we're going to change that to selenide. Each Se here is a -2 charge. -2 times 2 would be -4. One titanium can cancel the -4, means titanium is currently using its 4 charge. Again, it's just best to just assume here. You're not always going to be given it on the table. Titanium, we're going to use a Roman numeral for 4. When titanium uses its 4+ charge to bond against selenium, we're going to change the ending to selenide there. This next one here, don't be tempted to say nitrogen, hydrogen, carbon. Okay. It's usually just one part name for the metal, one part name for the non-metal. I told you definitely memorize most of the polyatomics, but definitely memorize the one that's positive. And this is the common name here, ammonium. So this one here is a grouping. It happens to overall have a charge, but since it has that common name already, I don't need to name that part myself. So ammonium, that means this Chukwu part here should be just a name in itself. You'll notice the Chukwu here is given 2 names. You could call it ethanoate. I can call it ammonium ethanoate. More commonly, however, we're going to call it acetate, so ammonium acetate. Both names are fine. Now going the other way here, it's a little bit harder because not only am I finding the symbols, I do need to work out the charges myself. Magnesium here is an alkali metal. Careful, magnesium is different from manganese. Manganese is a transition metal. Magnesium here is an alkali metal. Magnesium is in group 2, so magnesium, I'm going to change color for that here. Mg is a +2. We're going to see some naming later on that actually has prefixes here. This is still an ionic compound. It's a metal and a non-metal. What we're going to do here is the die actually does mean something, but that die was already in the name itself. That die, it has the AT ending, so it sort of indicates to me it's a polyatomic. You just look on the backside, and lo and behold, the name of dichromate, that common name, is actually this grouping here. So when magnesium is bonded to a grouping Cr2-2, we still need to work on the charges. How many magnesiums and how many charges do I want to cancel it out? Oh, just 1 and 1. So I can go MgCr2O7. So in that case, I just checked the chart there. The polyatomic dichromate was the Cr2O7 2-. I just canceled out the charges. Palladium fluoride. Again, be careful. Palladium is sometimes confused with platinum. Platinum here is down here. Palladium is 1 row above it. So palladium, they're actually helping you out. This looks confusing, but they're saying, oh, palladium is currently using its +2. What if it bonds with fluorine? Fluorine is a -1 charge. Again, not diatomic because it's not fluorine by itself. What ratio would I need to cancel it out? Hopefully you're able to say to me here PdF2. Again, all this just takes practice. And then for silver cyanide, we're going to find silver. Albeit it is a transition metal, we would expect it to have more than 1 charge. We're going to find that this one here is a exception. If you look on the backside, it isn't by chance that they actually only give you silver as 1 charge. Silver really only does have 1 charge, so I do not want to see silver 1 cyanide. If silver uses its +1, cyanide here is using its negative one. In that case there, it's going to be AgCN. So just get some practice going from the formulas to the word names to the formulas. Again, the challenging bit is it's just all mixed up together. While I have it on the table here, notice again most of our polyatomics are in this anion section. So for the time being, you can just refer to it. You will eventually need to memorize these. Most of these endings are going to be either ATE or ITE. There's a couple ITEs here, sulfite, nitrite, something like that. They already have endings. Don't change it to IDE. If it says IDE here, I'm probably thinking it's element. There are a few polyatomics that are a little bit weird. Hydroxide actually ends as IDE. That's not an element. That's the OH grouping. Cyanide, we just did, also ends in IDE. So just take the ending exactly as you see them. They do say in terms of memorizing polyatomics, you should memorize definitely the oxides of carbon, sulfur, nitrogen, I don't know what else, but in this case here we have carbonate, right? So memorize that grouping with the charge here. Memorize things like nitrate. We're going to see some patterns between the AT and ITE form in a second here. Phosphate, sulfate here. And you'll notice if you've memorized those ones, what is hydrogen carbonate then? Well, hydrogen itself would have an H+. If carbonate has a CO3 minus 2, if I bond that H+ with the CO3, the grouping is now HCO3, and now my charge has gone down by 1. So if you know sort of the main ones here, you can probably deduce what the other ones are going to be. So for the time being, you can still use the screen chart here. I actually printed it on green. Hopefully you'll be able to see that. But you're just going to use it for the time being and name your compounds. Today we're going to just throw in the last couple categories. So group number 4. So far we've done a binary compound, just a straight metal, non-metal. We threw in a multivalent as group 2. Group 3 is going to be polyatomics. This one here is our 4th category. Let's switch over and take a look at naming of acids. We're going to spend a whole chapter in grade 12 actually looking at acids and bases. For the time being, we're going to use the definition that we're familiar with. Acids will usually have an H, and they have to be able to release this H+ in solution. So not only do you have to hold an H is usually going to be the first part of the compound, H something. I usually just say HA, HCl, HBr, H2SO4, H or something, and it has to not only have this H, it has to, when dissolved in water, it has to be able to release this H+ in solution when it gets dropped in water. So this one here is the acid compound. Let's talk about naming of acids here. There's a few sort of subcategories of acids. First thing we can have is we can have binary acids. So as that name suggests here, binary means it's a 2-part acid. A 2-part acid will have the general formula hydro something ic acid. So let's do 2 to practice here. HCl and HI. At first, you would have just named it with a regular old ionic naming. You would have named it, well, hydrogen is the name for the H. The Cl here is going to be chloride, so hydrogen chloride like that. Because now we recognize, oh, this is a compound that starts off with H. If it's ionic, pretty much it's going to be an acid as well. I need to switch it over to the acid name, so don't leave it like hydrogen chloride. You're actually going to switch it over here. The hydro will represent the hydrogen, so I don't need to write out the whole word hydro anymore. And the blank is actually what's the counterbalancing nonmetal. In this case here, it's actually chlorine. So this one here is actually going to be hydrochloric acid. This is actually our stomach acid and actually dissolving food. So HCl. HI, we would have called it hydrogen iodide. We're going to then switch it over to hydro. Sounds funny, but hydroiodic acid. So hydro for the hydrogen bit, and the nonmetal is just given by that blank there. So if it is an acid, you have to convert it to the acid name. It's incorrect if you just leave it hydrogen chloride, hydrogen iodide. Now, the more interesting acids here is when we actually throw in those polyatomics again. As I mentioned, polyatomics have a general ending. Most of them will end in ATE. If the acid is built off a polyatomic that ends in ATE, we're going to drop the hydro altogether, and we're just going to be left with the ic acid part. So let's just do here. Let's look up our chart here. What's NO3 minus? NO3 minus here, the polyatomic grouping itself is nitrate. It has the ATE ending. Note this guy here is not the acid yet. An acid has to have the H+, because H is a positive 1 charge. How many do I need to counterbalance it? Well, if I have HNO3, where I would have otherwise called it hydrogen nitrate, again, I'm not going to leave it with just a regular ionic naming because I recognize this to be an acid. I'm going to drop the hydro altogether. I'm still told it is an acid, so I would imagine that it still has an H, but I'm just going to change the ending. Instead of ATE, I'm going to change it to nitric acid. So if the polyatomic would have been ATE, we convert it over to ic acid. Let's do one more here. Let's go sulfate. Again, eventually you want to memorize all these polyatomics. Sulfate sometimes spelled with an F, sometimes spelled with a PH, but more importantly here is the ATE ending. How many H's would I need to acidify it to get the protonated form? In this case here, we would need 2 H's, right? Enough H's so that the compound can be neutral. In general, we're done with the H's here. I wouldn't want to be H3SO4 plus because I just want to cancel out the charges. So I have this one here. I would have called it hydrogen sulfate. We're going to drop the hydro altogether, and we're going to call it, although you could call it sulfic acid, more commonly here is known as sulfuric acid. Again, spelled with an F or PH, doesn't really matter. So it's the acid that comes from the sulfate compound. Let's compare these two here. The other common ending for polyatomics is actually ending in ITE. If you look at the grouping here, NO2 minus on your polyatomic sheet, or SO3 minus 2, first thing you're going to realize here is, well, the polyatomic itself is actually covalently bonded. It's a non-metal. Because we're doing more sharing of electrons, we can have any number of ratios. When NO3 groups together, they have a -1 charge. When I'm down in oxygen, I still have a -1 charge. So that's a pattern that you can see there. In this case here, NO2 would actually be nitrite. SO3 minus 2 is actually going to be sulfite. So those already had common endings. Again, they're not the acids until I actually include the H's. So let's include the H's on the top one. HNO2 or H2SO3. This time, the common name, the ite, is going to, again, drop the hydro. It's still told it's an acid, but I'm going to change the ending to OUS acid, so something us acid. So in this case here, where you would have called this one here hydrogen nitrite, I'm going to convert it directly over to the acid name here. I'm going to drop the hydro altogether, and I'm going to call it nitrous acid. H2SO3 came from the ITE form, so this one here is going to likewise be called sulfurous acid. Probably harder going the opposite way, so if you're recognizing, if I say, oh, I have chlorous acid, what's the symbols? You would need to recognize, oh, the OUS would have come from the ite form, and then you need to match up what the polyatomic grouping with the ite form actually is. We're just recognizing patterns here. We're going to see the ate form is in some sense bigger than the ite form. The ate form actually has one additional oxygen, NO3, NO2. Sulfate is SO4, SO3. So the ate form is somehow bigger than the ite form. And in the same way, the ending, the ic form is bigger than the us form. So the ic usually refers to it somewhat a little bit larger. Just as a quick aside here, while we're doing patterns here, as you look on your polyatomic sheet here, unfortunately, you actually have ClO4 minus, ClO3 minus, ClO2 minus, and ClO minus. All of them are potential polyatomic compounds. This middle one here is actually called chlorate. So what would the acid for that one be called? In that case there, I put on the H because H is a positive charge. I need to counterbalance that charge there. The ending ATE should become chloric acid. Fine, no problem. This ClO2 is down by an oxygen. I'd imagine that it's the chlorite form. Again, the acidified form is with the hydrogen. HClO2, you want to be really careful with how many Cl's you actually have there, whether it's chlorate or whatever. In this case here, we call that chlorous acid. So that's fine. That all falls nicely with our pattern. But what if I now have this polyatomic that actually has even more than the ate form, or even less than the ite form? Here, if you look at the common name, these are already given to you. This is not something that I add to it. We're going to actually find that this guy here is actually called perchlorate. And that per prefix actually already tells you it's even bigger than the ate form. So if I have the acidified form HClO4, this one here is now going to be called perchloric acid. We still are changing the ending ATE to the ic acid, but that per in front that they've added for you actually tells you it's even bigger. On the bottom side here, what's even smaller than the ite form, we can actually say hypochlorite. That's the name of that grouping there. So if I have HClO, this one here is called hypochlorous acid. So you see, IUPAC has basically gone through trying to do some patterns so it's easier to memorize, but they've added things like per. We see permanganate. Hypo actually means less than. In fact, for these acids here, this is another common question of theirs, they might say, which of these compounds here contain both ionic and covalent compounds? Ionic and covalent bonds. In this case here, the ionic part, let's just focus on this compound here, HClO. The ionic part is between H with a plus and ClO together as a grouping is negative. So in that case there, sure. The plus and the negative, that one represents an ionic bond. That's ending up going to form a lattice. That's ending up going to cancel out the charges. But what about this ClO? ClO, we're going to see towards the end of this lesson here, is non-metal, non-metal. When they bond together, that's actually a covalent compound. So pretty much a polyatomic will always be covalently bonded. When I drop this in water, water is not strong enough to chop apart the covalent compound. Water is only strong enough to separate the positive from the negative. So if you're ever asked the question, which of these compounds contain both ionic bonding and covalent bonding, you're looking for a compound that has a polyatomic inside it. All right, so moving on now, let's go to sort of category number 5. We spend a lot of time looking at naming of acids. There's no real surprise with naming of bases. It's just whatever hydroxide, lithium hydroxide, sodium hydroxide. That part there is very different. Category 5 here, we're going to throw in, this one might be a new family. Acids may have been new as well, but we're going to have hydrates. When something in just everyday life is hydrated, we say it has a lot of water inside. So hydrate are a name of a species. Species is a generic word for a thing or a chemical. It's a species that holds or it contains water. Hopefully we'll be able to do a lab here to actually figure out how many waters there are. In this case here, we're just trying to figure out how do we name this species. So what I want you to do is imagine with me here, let's start off with a compound here, CuSO4. So far, all our compounds have been what I refer to as anhydrous. Right? That prefix an or a something usually means not hydrous. So anhydrous is another name of saying dry. This dry compound here is a lattice. This one here is made out of copper parts. I'm not going to fully draw the sulfate part, but I know it hangs out as a group. It's that covalently bonded. Because it is an ionic bond, I expect it to form a lattice. In that case there, that's just my anhydrous compound. We'll call this one here copper 2 sulfate. You should be able to explain to me why there's that 2 there. So far that's dry. What I want to point out in this picture here is this lattice that repeats sort of over and over in 3D space. You notice that there's actually pores, there's actually holes that are left behind. Those holes are usually big enough to actually hold actual water molecules. And that's exactly what's going to happen if you imagine this anhydrous compound to be a sponge. Imagine you have a pool of water just sitting there. As you drop this sponge here into the water, like a sponge, it soaks up all this water. Eventually, you lift your sponge out. We're going to still have, so you put it into the water and then you lift it out. We're going to have the copper structure here still stay together. So copper, we still have that lattice structure we had from earlier. But all that's happened now is we're going to actually have embedded some water molecules are actually filling in the gaps here. One thing I want to emphasize here is this is the hydrated form, sure. I'm going to use the compound CuSO4. In the symbols, we're going to have a dot. It almost looks like a multiply. Dot 5 waters. We'll come back with a pretty easy experiment. We can actually figure out what that number is. But again, for the time being, I'm just trying to identify how do we name this compound. So it's sort of saying here, my dry compound, my otherwise copper 2 sulfate, that part there doesn't change. This one here has become hydrated because it now contains water. It's now soaked up with water. So hydrated, it contains water in those holes, in those gaps that are left behind, in those spaces. And in this case here, in terms of our naming, this is the first and only time in an ionic compound we're going to add prefixes. So in the general naming of this one here, we're going to use prefixes. I'll jump through the prefixes with you as we switch over to covalent. Use prefixes to show the number of waters. And again, for ionic compounds, it's always a ratio. So I know even though I write CuSO4, that just represents one, for every 1 copper, there's 1 sulfate. In reality, there's gajillions of coppers, gajillions of sulfate. In the same sense, though, for every 1 part copper, 1 part sulfate, there happen to be 5 times as much water. So we're going to use the prefix penta, like pentagon. We're going to remind ourselves that it's a hydrate family, so it's going to be pentahydrate. Sometimes I get a really funny ending here. I get some things like pentahydride, pentahydrogen, pentawater. Just remember we are in the family of hydrates, so just leave the ending as AT. The thing I want to emphasize before we leave this one is the hydrate is still a solid. For this one here to actually hold water inside, the lattice itself has to stick together. For a lot of ionic compounds, when you drop them in water, it doesn't stay solid. It actually dissolves and breaks up. By the time it dissolves, if I have copper ions by itself and sulfate ions by itself, when it's dissociated, there's no way I can form a hydrate. There's no way I have a lattice structure left over. There's no way I can end up holding water. So a hydrate is still solid. Make a note to yourself. Okay, so in that case there, let me just introduce some words here. There are 5 waters per every 1 CuSO4. Maybe I have a billion CuSO4s. That means I have 5 billion waters, at least by ratio, it's just 1 to 5. That really is the only time we want to show prefaces. The trouble here is, as we switch over to covalent, we're going to see prefaces are so easy to work with that sometimes, unfortunately, we would go back and we'd say, oh, hey, there's H2, dihydrogen, or, oh, there's earlier when we were naming compounds, oh, there's a Se2, diselenium, cesium. You notice that we were able to name all this ionic compound here without prefaces. It's actually incorrect for you to actually use prefaces. Prefaces are actually a good way to actually hint at it's probably not ionic anymore. The only time we saw prefaces, like I mentioned for hydrates, for ionic, I want you to do a really, really big line in your notes. Basically, this is sort of separating us from ionic, and we're going to have our first look at covalent compounds. So for a covalent compound, couple key differences. This is sort of the other extreme in bonding. Ionic was one side. For a covalent compound, we're expecting to see a non-metal bonded with a non-metal. Remember, non-metals are on the right-hand side of the table. We don't have as many, so the choices are not as great. However, we're going to see between the non-metals, both of them are fairly small atoms, and because of that, they're going to typically end up sharing electrons. No one is really willing to lose electrons. Because there's no charges, we actually don't form a lattice. These ones here are typically called individual molecules, or just more simply here, we can just say molecular. So when I really show you this compound here, when I do a compound like CO2, I really mean just one carbon somehow bonded to 2 oxygens. It's not, oh, by the way, it's a lattice, or by the way, it actually repeats, or whatever. It is just the single molecules, just a single grouping, as you might imagine. So you can either say individual molecules, just right there. You can say individual, or you can refer to it as molecular. It's just the one species. Now, the one confusing bit here is, normally when I'm thinking nonmetals, compounds like that, there are gases. Well, ionic compounds are solids. Ionic bonds must be stronger. The thing you have to be really careful here is, let's say I do have carbon dioxide as a gas. In this case here, I notice inside carbon dioxide, inside are the covalent bonds. But if I have a container full of carbon dioxide, this one here is a C with 2 O's, this one here is a C with 2 O's. In fact, as a gas, I haven't destroyed any covalent bond at all. The bonding that I've been separating is actually, here's an individual molecule, here's an individual molecule. Somehow they have intermolecular forces. Somehow they have some background forces. When I'm actually just trying to vaporize them, heat them enough so that they melt and they boil off, all I'm doing is I'm actually breaking these intermolecular forces. I'm not actually destroying a covalent bond. In fact, dollar for dollar, we're going to see in chapter 4, covalent bonds are actually stronger than ionic. It's just that it's not a fair comparison. Ionic compounds form lattices. There's many bonds. It's really hard to melt. In this case here, the covalent bond itself is actually fairly strong, but it turns out those in-between forces, intermolecular forces, are weak. We call these forces here London forces. Those London forces are really easy to melt off and break off, so these are typically going to be gases at room temperature. Again, more on all this later on. So we talk about sharing of electrons. We talk about them being individual or molecular. In this case here, there is only one rule for this. When we're naming these compounds, we're going to use prefaces, use those syllables that come before words to show the number of atoms present. No charges, no working out the charges so they cancel out, no lattice, no polyatomics, no acids or changing endings, anything like that. All we're going to do is we're going to use the appropriate prefix. So let's just count to 10 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are prefixes beyond that, but usually this is good enough for us here. Again, on your grade 10 tables, they just give you a listing of these here. These ones you do have to memorize. So mono for 1, di, tri. 4 is actually based off the root word tetrahedral. We'll see that structure in chapter 4. Tetra means 4. Penta we've already used up above for saying 5 waters. A hexagon, 6. There is such shape as a heptagon. It's just not a very symmetrical shape. That's why we don't usually talk about it much. An octagon, like a stop sign. Nona is 9. Careful, this is different from nano. Earlier, nano was the prefix 10 to the negative 9. Nona is actually the prefix for having 9. And in this case here, deca, if you've ever seen a decathlon, is a 10-activity sport. They usually do it sort of with Olympics, things like that. So, as I'm doing this naming here, we don't need to check charges. There aren't any charges. We just use the appropriate prefix to tell you how many there are. So let's say I have the compound here, CO and CO2. First thing you want to do is check, is it covalent or is it ionic? This one here is non-metal, it's covalent. In the order given, it's usually the less non-metal, the least non-metallic one, working your way to become more non-metallic over into that corner close by fluorine. We're going to name it here, well, there's one carbon, monocarbon. I wanted to say monooxide, so in this case here, they're actually going to, I just say monoxide. Again, IUPAC, which sort of sets the rules here. IUPAC says we can drop the first if it happens to be mono. So like this example here, the first one is mono, you can just call this here carbon monoxide. You notice I've still changed the ending to IDE. It just makes the non-metal easier to recognize and easier to say. So what would I call CO2 then? I would have called it monocarbon dioxide. Again, if the first one happens to be mono, you can just similarly call it carbon dioxide. Notice that in this case here, IUPAC says we can drop the first one. We are not allowed to drop the monoxide. You will find some textbooks actually, so keep this. So keep this mono. You'll find some incorrect textbooks actually say carbon oxide. That's actually not a correct IUPAC name. Let's do one more here, N4P7. I have no idea if these compounds exist, but if they did, I should be able to name them. So this one, the prefix for 4 is tetra. So we can say tetra nitrogen. So no IDE for the first nonmetal. The other one is 7, so we're going to say hepta. And this one here is phosphorus, so we're going to say heptaphosphide. Would I drop the tetra here? Well, of course not. The prefix is actually giving you, it's actually 4 to 7. It's only if the first one happens to be mono, then you drop it. So just for a quick challenge here, let's see if you can name H2C2O4.2 waters. Again, the hard part here is it's all mixed up. Oh no, I'm throwing those hydrates in. Oh no, it's an acid, things like that. Let's see if we can break apart this name here. This one here is ionic, so I'm not going to use prefixes for the entire thing. In this case here, that grouping there is the oxalate grouping. We are an acid because it's a hydrogen oxalate. The ATE ending ends up becoming oxalic acid. And this oxalic acid as a solid, as a lattice structure, it's ending adopting 2 waters. The prefix for 2 here is going to be di. The ending is going to be dihydrate. So that compound is called oxalic acid dihydrate. On your worksheet, you'll get a lot more practice with this. Making sure you're memorizing polyatomics eventually here because your IB data books won't have them. So just do some more practice and let me know if you have any questions. Thanks, guys.